recording. Thank you for joining the 28th San Diego C++ Meetup, and we have a very special guest today. I'll introduce him in a few seconds. First, just the few regular things that I would like to mention. First of all, the Meetup fees are paid by Qualcomm Wireless Research Department Software, which I'm part of. So thank you, Qualcomm, for paying the fees for the meetup and sponsoring and supporting the meetup. For today, we have a special agenda. We're hosting Fabrice from TrustInSoft company, which would present proving the absence of undefined behavior in C++ code. Fabrice and myself are in a very different time zone than San Diego. Fabrice is actually our third person. Hey, Fabrice. Fabrice is our third person from Europe. I don't know. I might be changing the name from San Diego C++ Meetup maybe to something like Eurovision C++ Meetup or something like that. Maybe in San Diego is not the right thing since we have so many people from Europe speaking. So, but jokes aside, let me introduce Fabrice. So Fabrice Derepas, he is the CEO and co-founder of the cybersecurity startup TrustInSoft. Fabrice got his start. He started in the telecom industry as a system architect, and then he worked as the CDO for startup companies. In 2003, Fabrice joined the CEA. It's a French technology research lab where he directed the business development and managed a department. He led programs and provided strategy for the CEA-LIST Institute. He holds a Ph.D. from University of Paris 7, as well as an engineering degree from the Ecole, I don't know if I pronounce it correctly, Polytechnique. So welcome, Fabrice, and thank you for the talk that you'll provide in a second. I'm going to stop presenting, and you can take it from here.
Okay, I'll do that. Thanks. Here we are. I think you should see my screen, hopefully.
Yeah, we can see your screen. We can hear you well.
Okay. So, just to start with a small quiz is, what do game consoles, smart meters, phones, airplane, and space probe have in common? The answer is all of sectors have some company who actually use what we do to make sure that the software they have does not crash. So I will try to explain how in those different industries they use us with like a lot of example. Hopefully that should be technical enough, so you will see a lot of C++ code and you will be happy. So if I want to prove a plus b to the square equals a to the square plus b to the square plus 2 times ab, actually you can't test this formula for all possible values. So the right way to do it is actually to perform some algebraic transformation so that you are sure that for any couple A and B, this is going to hold. So actually, we are going to do just that, but we'll be doing that on software, and we will not be doing that on mathematical formulas. So in order to reach this level of quality, there are two topics that we need to address. The first one is removing the undefined behavior, and the second one is ensuring the functional proof. So functional proof, I mean that a function f or a method is actually doing what it's supposed to do. So if we focus first on undefined behavior, have like two stuff. Is first, you should test your software. This is like good practice. This is number one. And then we are going to see how we can do exhaustive test, which roughly is what we discuss with the a plus b to the square. And then this is going to be the third part in my talk. We are going to talk of how can we functionally prove that the function really does what it's supposed to do. And here you will see some example. So first, I'm sure all of you know that, but this is the definition I really enjoy. But it's a definition of an undefined behavior. It's somebody once told me that in a basketball, you can't hold the ball and run. I got a basketball and I tried and it worked just fine. So he obviously did not understand basketball. So it might sound funny, but actually, regularly some developers say, oh, I don't care, I have an undefined behavior, but the program is doing just what I wanted to do. Good for you, but actually this is just sheer luck. So you can't expect the program to work like in the next version of the compiler, or it's very unlikely that this is going to stay in the future. So if we take the official definition from the C++ standard, actually an undefined behavior is a behavior for which the norm actually does not impose any requirements. So because you have no requirements, maybe you're lucky it does what you expect, but maybe this luck could change in the future. And undefined behavior, especially buffer overflows, are used by hackers, so that doesn't sound like something good. It's very different because we're in the use of words. It's very different from unspecified behavior, which is also specified in the norm, which would be like architecture-dependent features, such as, for instance, the size of integers. So we are going to start with a small quiz. So you have an undefined behavior in this program, and you will see indeed that we get two fairly different behavior from this piece of code. So I got a function f, takes a pointer to an integer, pointer to a float. Then I write 1 in the integer location, 2.0 in the floating point location, and I return star p. Then I have my main function, local variable I, and I display the result of f called with a pointer to I, the pointer to I casted into a float. So if I actually run this program, I get this like big number. And if I run the exact same program with -02, I get 1. So it really looks like with the same program, I have two very different behaviors. So you could say, oh, there's a bug in clone, but if actually you took JCC, you will have the exact same result. So why is that? So typically, if we use a TrustInSoft analyzer to actually kind of compile the code, this is how it works. So it works roughly like a compiler. So you have the command line, which is right here. So instead of clone++ or G++, you have tanalyzer++. And you mention the list of compilation units that you want to bundle together. So it's roughly like a link face that your compiler has. And if you look here, what you have, if you have it's a warning, it's not an error, is the pointer q as type float star, it violates the strict aliasing rule, indeed, because the strict aliasing rule said that two pointers of different types should not point to the same memory location. And the thing is, some compilers, they use that to perform some optimization, which totally makes sense, which is what happened here. So when we have no optimization, indeed here, we write 1 and we write 2.0 at the same memory location. But when you optimize, the compilers know that you are a good programmer. Because you're a good programmer, you do respect strict aliasing, and because you do respect strict aliasing, it means that somehow it's impossible that P and Q point to the same memory location. So the compilers actually write for real that F always returns 1. Just to give a some idea, so why it's bad to do, but I'm sure you knew it, but this is an example I really love. So what we put online is we put online a small tool. It's called tsnip@trustinsoft.com. It's a tool I use regularly for myself. It enables to really understand what's going on in a small snippet of code. The undefined behavior I just showed to you is not in the online versions. We don't have all the features in the online version, so the one is not working, but I'll show you some two examples. So we can use it to determine some UBs. So here, for instance, I have like a vector V, I push some number, and I want to iterate on the list. At the same time, I want to remove places where I have 4, which definitely is a bad idea. I know that. You should not do that. I'm sure you knew it. So typically, if I cut and paste the code in Tsnip or TrustInSoft.com, actually, I'll be able to get that, and this is going to point me directly where the issue is. So we model big deals of, here you can choose your version of C++, you can choose C++ 11, C++ 17, C++ 14, C++ 20. We're currently implementing the features in C++ 20 as they appear in Clang. I also use it fairly often, Tsnip, to actually understand a piece of code. So here, a short example, I got a struct here, point 2 bit fields, X and Y, with 3 bits, value 3, value 4. And here I got like something, a lambda function, and I just want to see what it returns. So I could actually, of course, just compile it. I will have the answer. But let's assume that actually I want to understand why the answer is 0. So here, when I run TrustInSoft Tsnip, actually it says, oh, the return value is 0, which indeed was the case. So if I click on R, I'm going to see the value. In the bottom right of the screen, you can see the value is 2. P of X, its value is also 2. This is why 1 minus the other equals to 0. Then I click on the lambda function. I'm going to be inside the lambda function. I can see the value of X, Y, and TMP. So that really enables to understand what's going on. So we see that actually the value X is equal to 3. And I add actually the value Y, which strange enough was -4 because I was a bit field of 3. And if you put 4, that actually turns to -4 because I just have 3 bits. So that's 3 plus -4 plus 3 again. So that actually is 6 minus 4. So that's 2. This is why R is equal to 2. And because actually we pass P as a reference here to in the lambda function, we can see that indeed, and we decrease the value of P dot X. So actually, P dot X becomes equal to 2 as well. So this is why R minus P dot X is equal to 0 in the end. So small tool, fairly simple, easy to use. This is the way when I say, okay, it's important to test, this is exactly the kind of stuff we do. So we can do that on, of course, larger programs. So we can do that on several, like hundreds of thousands of lines of code. It's not online yet, but in the levels to really test all the possible behavior and enhance the test. Because at this level, we'll be able to get all the possible undefined behavior that you have in your existing test. So sometimes you got some undefined behavior and you're lucky, you don't see them, or maybe you're lucky, I don't know what I should say, but that's somehow what's happening. I'm sorry, my camera just froze. So here, now I'm going to switch to the exhaustive test. So exhaustive test, we are going to start with a toy example. So we are going to perform like a lot of tests. We are going to perform this number of tests. And we are going to do that on a standard computer because this will be on my laptop. It's a video I shoot, but I shoot the video on my laptop. So we are going to do that on a small example, which is the scissor cipher. So the scissor cipher is fairly, I could say, a dumb coding algorithm. Dumb because we have huge algorithm now. It was not that dumb maybe 2,000 years ago. The idea is actually to apply an offset to the letters, and we apply the same offset to all the letters. So here, for instance, you have a scissor. So C, if you add 3, that becomes F. A, that becomes D, this kind of things. So here, for instance, I implement the scissor cipher in a class named scissor. So you can see that I have the offset, which is the parameter. It's a template class with the type actually of data I'm manipulating. Here I encrypt a buffer and I return a shared pointer. And here I decrypt a buffer and I return a shared pointer. And you can see here in the private methods have an absolute int method. So the code is fairly simple. So Caesar encrypt actually so takes the buffer, the size of the buffer, and the offset. So I compute the absolute value of the offset. And then I get the crypted buffer here, which is the shared pointer, which points to an array of size sz of type t. And here I have my destructors. Here, then I go in all the letters in the word, and I add the shift to have plus shift, so hopefully it looks like it's doing what it's supposed to do. Then I have the decrypt function, which does exactly the opposite. So I have a minus sign instead of a plus sign. And here there was my absolute integer function, which actually takes an integer x. If x is below 0, I return minus x, otherwise I return x. So this was kind of, you could say, my library test. So now I'm doing 2 tests because 2 it's already a big number. So here, how to do one test? So gen test, actually I call encrypt, and afterwards I call decrypt. Then I have my main function, which gets like some random buffer, like people of your attention please, and I apply an offset of -3 and +7. So if I run this code, indeed, this is just a screenshot. Actually, you'll see that it does some encryption and I have like a different encryption for the offset +7. So it looks like everything is working fine. So first, what I would like to do is I would like to test this library for any possible offset. So any possible offset, it means 2 to the power 64-bit, because here the architecture I'm using is a 64-bit architecture. This is something that you can change in the tool. So here, the way to test all the possible integers, you'll see it's fairly simple. I just recall how I do the test for -3. I call gen test with -3, gen test with +7, which is just what I showed to you before. So to do it for any possible integer, then I just need to declare a local variable named user_shift, and there's a specific function which name is tsMakeUnknown. So tsMakeUnknown, it means that we are going to have all the possible values in the given type. In here, the type of user_shift is int, so it means any value from int min to int max. So I just give as 2 arguments to tsMakeUnknown. I give the address of user_shift and the size of the integer. And then now, actually, user_shift is not a number anymore. It's an interval. And even though it's an interval, I can use it as if it was a single number. So I can pass it as an argument to gen test. Okay. So now, if I run the tool, I'm just going to show you what it looks like. So I change to the good repository, and I call make TIS, which is roughly the same command line that I showed to you before. Here, I'm using the graphical user interface, so it launches locally a web server. So this is it. The web server is here. So now I'm going to switch locally on my browser to connect and see what's going on. So it's done. So it just did 2 to the power 64 test. It just did it. So here on the right, this is the original C code I've been showing to you before. In the middle window, this is like a clickable version of the code where some extra commands have been added by the tool. And on the left, here you have like a summary of the analysis. Here you have one undefined behavior. So you can see that the undefined behavior is when I'm computing -x to compute the absolute value. And here the assert has been automatically added by the tool. This is the way actually the tool talks to me by adding those comments in the code. So here -x should be below like a big number. So On computers, you have more negative numbers than positive numbers. It goes from minus 128 to plus 127 for 8-bit numbers. And of course, this is the same for standard integers. So here, I can't compute the opposite of the minimum integer. So this is an error. So either I should return some random value, or I should not call the absolute value with the minimum integer, but whichever solution is the right one, definitely this is not the right one. So now I would like to extend to two tests for any offsets to 2 to the power 64 minus 1, because I can't test for the minimum integer. And I would like to do this on my original buffer, which was a size 38. So I would like to do 256 to the power 38 times all the possible offsets. So it's like really a big number. This is the number I've been showing to you before. And actually, the way to test it is like exactly the same, and it takes exactly 1 second to do it as well. And the way to do it, this is with this kind of code. So here you have user shift as you saw before. And now I just need to call Tsnip unknown on the buffer, which is str. So it means that each byte in the buffer will be any possible byte. So here you can see that indeed I'm calling Caesar encrypt and Caesar decrypt. And just by doing that, I'm able to do exactly the equivalent of the number of tests which was written before. Of course, it's impossible to do this number of tests, so I'm not doing the number of tests, but I'm doing a computation exactly like a plus b to the square. I'm sure that I will not miss any issue. And this is why actually we come from safety critical industries. So now we have some people using us even for consumer electronics, but definitely this comes from safety critical industry, where we had no choice but to make sure that we test any possible behaviors, and also we are able to show that to some regulatory bodies. So I just have been showing to you this small example, but you could say, okay, it's nice, Fabrice, but you did it on purpose, which is true, and it's very small. So I'm going to show to you some example. I call real life example, some stuff we did for real and that I use. So first example, of course, I'm only using open source example because our customers tend not to be super fan of disclosing exactly what they're doing. So only open source code. So Apollo, it's Apollo.auto. It's an open source platform which enables to actually create autonomous cars. So you can download it and like do your own autonomous car. So if you got some tests, this is what is represented here by the points. You do like some points. When you do an abstract test, somehow you are checking all possible values. Here, for instance, if you got the floating point numbers, we are able to test all the values for all floating point numbers in a given interval. And if we have two of those values, because PNC map is actually, for autonomous car, is handling a real map, which the car is going to use to make decisions, should I go right, should I go left, the kind of stuff, then we need to test for any possible values that is read from the map. So we actually validate fully the absence of undefined behavior on small squares. And you can see that here, actually, we are able to cover the road with a lot of squares. And at the end, we have a guarantee that whichever value is read from the map, never ever the C++ code which actually drives the car will have an undefined behavior. So just to give an idea of a feeling of how it works, so you remember in the former example with the Caesar cipher, we talked about like Tsnip unknown. Here we have another function which name is Tsnip double interval, which means that we're gonna get all the double numbers which are in a given interval. So typically here, you can see that if you really want to compute like an approximation of the number of tests, which is equivalent to testing all the possible double numbers in an interval, this is like this number of tests, which is like fairly large. So this was really like some kind of applicative software. Here I have the same example, like on a, just right below on communication stack. This is a stack from ARM. It's open source. Its name is ARM Embed. And the NIST, in a report to the White House, actually explained that indeed TrustInSoft was able to formally guarantee the absence of all of the CWDs which are here. And we have a full report. It's a 100-page document which has been generated automatically in part, with details how actually which are the guarantees that you can have on the source code once actually TrustInSoft Analyzer has been running on it. So we did applicative of communication, then we go one level below, we'll go another example. It's a Linux kernel driver. So of course, when a Linux, so here, I'm sorry, this is not C++, this is just C. So if you have a piece of C code which is in a kernel driver and it crashes, this is bad because it's very likely that your whole system is going to freeze. And when you do some tests, sometimes you're not able to cover every values that the hardware is going to give to you. So when actually you use TrustInSoft on a module of the Linux kernel, you are able to say, oh, whichever value is going to be given by the hardware, even if there's a defect in the hardware, we are sure that never, ever the driver is going to crash, because we don't have undefined behaviors like buffer overflow typically. So I know that for several people, it sounds like magic. Like, okay, how are you able to do this number of tests? So just a quick explanation. The framework that we have at TrustInSoft enables to have different formal methods to collaborate together. And generally, the results you'll be seeing comes from the collaboration between the different plugins. Here, the plugin which is used the most is actually abstract interpretation. So I'm sorry, this is a cut and paste. I didn't know the picture. The picture is from Patrick Cuzo's course at MIT. The goal of this slide is to explain how we did it, like how that works internally for the TrustInSoft Analyzer. So let's imagine that you got several executions, like you got the green execution, the yellow execution, the red execution. And you got the forbidden zones. So of course, what we do model by default at the forbidden zones are all the undefined behaviors, exactly like a compiler would use an undefined behavior, for instance. Then what you want to make sure is you want to make sure that you don't have any potential behavior which is going to go in the forbidden zones. You don't want that. So what we are going to do is we are going to say that, okay, all the possible trajectories are actually going to remain in the green zone, and never ever the green zone is going to touch the red. And by doing that, we'll be sure that indeed no trajectories will have an undefined behavior. The thing is, if you count the number of points you need to describe the green shape, it's way smaller than the number of points to describe all the possible trajectories. Typically, here I got like 1, 2, 3, 5, 6, that's like 6 points in the top, 6 points in the bottom, plus 4 points for the square, so that's 16, plus 2 points for the circle, and that should be like 18 points. So with just 18 points, I'm able to describe a subset of all the possible behavior, which is way simpler than having all the trajectories. And this is why actually we're able to say, oh, we do the equivalent of this number of tests and we have huge numbers, because actually we are doing that. So now I'm going to jump to the third part of my talk, which is the functional proof. So it's important to do it in this order. So that is, first, you remove the undefined behavior. So you are sure that indeed your program behaves, I would say, in a deterministic manner. We didn't talk about parallelism and stuff like that, but we can do that some future session if this is something in which you are interested. So, but let's dive in the functional proof. So this kind of techniques were developed initially in partnership with Airbus in the aeronautic industry. And we have a nice IEEE article which explains how to deploy TrustInSoft in this kind of environment. And Benjamin Nutt, who is the CTO and co-founder of TrustInSoft, is actually a co-author of this article. It was a while ago, it was like 10 years ago, yeah, 8 years. So if it's just like a more notice. So if what I'm going to show to you scares you, it just means that it's not for you, but you don't have to scream, of course. So what we have is we are going to annotate the code using some comments. And this is where actually it's very interesting, but it might take, of course, a lot of time. So if you don't already spend a lot of time testing your code, it's very likely that these kind of methods are not for you. It's based on the concept of contract. So somehow you could say that we're extending C and C++ by adding some contract. And we'll be able to specify some functional properties expected by the function. And by the way, ACSL is also the language which is used internally for all the different plugins to communicate together. So remember, we got several different formal methods. We have a set of plugins which enables to implement the formal methods, and ACSL is also the language between all the plugins. So which are the components that we are going to use to annotate the code? So first, we have first order logic, like for all or exist. Then we'll have, of course, the C and C++ expression or types, like integer, float, or classes. And we'll be able to manipulate concepts such as relative integers or real numbers. And of course, because especially in C++, we tend to have a lot of stuff around memories and pointers, we have a lot of built-in predicates and logic functions over pointers. So we talked about the, I would say, big example. This is exactly the kind of stuff that has been done for like in the aeronautic industry. This also, we have some people using it in the smart metering industry. So we have more and more people using this kind of stuff. So first, I'm going to first detail a class. The class is going to check that have only zeros in an array. So this is a templated class. So I define n as a template argument to class A. And here you can see that I have a method, check all zeros, have a local variable k, and for k between 0 and n minus 1, if k at index, if t at index k is not equal to 0, I return 0, otherwise I return 1. And t indeed is an array of size n, which is the template argument, and with integers. So now what we are going to do, I'm going to push in different corners the C++ code, and we are going to fill in the gaps with some comments, which gonna be somehow the specification I'm going to add to my C++ code. So first, we are going to add a class invariant. So the class invariant is going something which is always true. So here, I assume I name this class invariant POS, and it says that indeed n should be always positive, and t should be a valid pointer from 0 to n minus 1. So it means that if at some point I'm instantiating a with a negative number, then TrustInSoft analyzer is going to complain and say, oh, what the hell is that? It's not possible. You do not have the right to instantiate a with a negative number. Then we have here a post condition. So we have the method check all zeros, and somehow we are going to write a specification to make sure that it's always true. So I did not mention assigns nothing here what it is, but somehow assigns nothing, what it does, it enables to make sure that no global variable is going to, or field in class A is going to be modified by the method check all zero. So if at some point check zeros is modifying a global variable or it modifies a field in class A, TrustInSoft is going to complain and say, oh, what the hell is that? You do not have the right to say and to do that because actually it was written assigns backslash nothing, which means that you should not assign a global variable or a field in class A. And then ensures here, ensures is actually the post condition. So it's a mathematical property which should be true when you return from check or zeros. So basically what it says is backslash result, which means the result returned by the method check or zeros is not equal to 0, is mathematically equivalent. So inferior, equal, superior is the thing equivalent to for all relative integer j. So j, basically, it has no bound. This is really a relative integer, so any value possible. So it's really a mathematical object. For j between 0 and n minus 1, so here, this is really funny because n is actually an int from C++, and j is a mathematical relative integer. And I think it's really cool to actually be able to, in the same sentence, almost to talk about the two. So here somehow, for j in this range, it means that t at index j is going to be equal to 0. So this is kind of a specification, and what we are going to prove, we are going to prove that actually this mathematical property holds given the invariant that we have for the class, which is right here. For this to work, actually, we need to add some extra lines. This is, I call that the helpers. So these are some loop invariants which enables the proof to work by itself. So here we are going to say that we have a loop invariant, which is k is always between the bounds of the loop. Here another invariant is we have only 0 between the beginning and where we are now. We assign, only one variable, which is k. And we have one variant. A variant is a positive number which decreases at each turn in the loop. So here, the idea is n minus k is indeed a variant. So these are some annotations. So it's just a comment. So when you compile the code, of course, that does not change the behavior of the code. So now if I put this in TrustInSoft Analyzer, so I'm going to just list the files. I have t.cc and my make file. So if I launch TrustInSoft Analyzer exactly the way I used to do it, here it does the same thing. It launches the web browser. I'm going to reload my web browser, and I'm going to right click on the stuff to display. And here what you can see is you have only green bullets in the margin, which means that all the properties are true. You have two properties which are not true, which are the one with the blue circle, which should be like right here, the blue circles. And why it's not true? It's not false either, but we didn't prove them because actually we called the method check all zeros without any context. So here the requires you should make sure that indeed here the pointer to this is valid. And because here we didn't call any constructor as well, it says we should make sure that the pointer should be valid. If actually we were calling the main entry point where we instantiate some variable, those properties would be proven. So it looks magic, it looks wonderful, like, okay, I'm pushing a button and I'm proving some mathematical properties. But of course, you bet that this is not going to work each and every time. As soon as you have some mathematical properties, which is a bit complicated, TrustInSoft is not going to automatically prove it by just hitting a button like run. So when it's not possible, actually, we are going to generate some small program and which will be proof obligation. And once the proof obligation have been proven, then we can say, okay, we are sure that the global property on the C and C++ code actually holds. And in order to do the proof, we can use some proof assistants which are mentioned here, like PVS, Croc, or Isabelle HOL, which are fairly well-known tools for the people who do these kind of activities. That's it. 40 minutes since I started to talk. It's time to wrap up. So the thing to remember, the analysis starts from the entry point. So basically, we do it like a test. We can, on the existing test you have, find some undefined behavior, which proves to be a very, very useful because you have nothing to do. You just push the button, you rerun your test, and you have, I would say, bugs for free, some undefined behavior which were here and you were not aware of that. And we did that on many open source code or code of customers, and it proves to be extremely useful. This is stage one. This is what I described. Then we have stage two, where we are able to have an exhaustive test coverage. So we can say, whatever happens, we're able to handle the possible behavior. And this is when the NIST in the report to White House says TrustInSoft is able to guarantee that you don't have any 0 days in SSL stack. This is exactly this kind of stuff. So we do that from C and C++ up to C++20. And we can go even up to a functional proof if this is something you really want to do, but it's kind of costly, even if the benefits are huge. The platform, I didn't talk too much about that, but of course we can have different platforms because we do not compile the code, we interpret the code somehow, and we need to have, of course, a description of the platform, like the size of integers, the padding in the structures, the endianness of the platform you have. And we can use, as I showed on some small example, we can use like an universal forward or backwards way of navigating the code, which gives an incredible insight on how your software actually behaves. And that's it for me today. Thanks for listening to me, and don't hesitate to ask the questions you might have.
Thank you. Thank you so much, Fabrice. It was very interesting. I really enjoyed it. And I think we have time. We'll open the floor for questions. So go ahead, and if you have a question, please chime in. Yeah, Michael, it seems like you have a question.
Yeah.
Go
can
ahead.
you guys hear me? Yeah. Okay, so I was just wondering, for the newer C++ versions that are going to come out, like for C++ contracts, how would this work with that? How would it meld with contracts if it got accepted into the standard? Any ideas?
So we tend to be fairly pragmatic people. So when it will be actually integrated in the standard, and it will be also in the field with the compiler. So when it will be in Clang, we will have it, and we support this kind of features.
Okay.
The idea is somehow we follow the compilers, and we can't afford, I would say, to be ahead of Clang, because developing Clang is like a lot of work. So I would say we follow Clang or the most advanced compiler at the time. And this is basically our strategy.
Gotcha.
Thank you, Michael. Any other questions?
So like, can you give us like an idea of like the kind of like techniques that the engine is using? I know ACL2 uses like from the Lisp world, they use mathematical induction. Is there like anything more beneficial for TIS like that TIS is bringing to the table? I'm just wondering what makes it different.
So we have many plugins, and we have a wide variety of plugins. Some are like super alpha, some are like super mature. We have 3 plugins that we use really like a lot. So we have the abstract interpretation. This is what I just showed to you with the trajectories. We have something I didn't talk about, which is the dependency analysis. We use that to do tented analysis and these kind of things. Or when you say like which function is actually accessing a memory zone in my program, we are able to say that only function G and function F are going to access this, and no other function is going to extract data from this. So we use a dependency analysis. And the last one is actually the WP, the weakest precondition, which is what we use actually when in the first stage I show you the functional proof. So these, I would say, are the three main things that we are using. And after that, we have lots of different other plugins. Typically, when we want to check if you have some undefined behavior on your existing tests, so without even doing the step 2 I was mentioning, but really a step 1, we have an interpreter mode actually that runs, and it's also a plugin. So we have a plugin also which is dedicated for multi-thread analysis. It doesn't work in the general case because working in the general case for multi-thread analysis is kind of difficult, but it works at least for the programs that our customers have.
Cool, thanks.
Thanks, Michael. I have a quick kind of a comment and another question. So first of all, if you have any reports that you can point the members to, if you have anything that you analyzed in the open source, obviously it's open source, but if you can maybe point us to such reports and we can read it and look at it. So that's one thing. A second thing, can you explain if there is any intersection between fuzzers, the word of fuzzers and the tool?
That's a good question. So first, Kobe, in my presentation, so you got the PDF that you can share, and you have a link to the Polar SSL report. So it's a report, it's a 100-page document which explains how we can make sure that we don't have buffer overflows in a communication stack. And this is open source, public, and you can download it, it's free. Then, okay. To answer your second question, the fuzzers, indeed, yes, using fuzzers is a good idea. So we have 3 levels. We have level 1 with the test, level 2 with general tests, so we don't need fuzzers, and level 3, functional proof. So this is actually with level 1. With level 1, we can be coupled typically with AFL. So we choose AFL, American Fuzzy Loop, because actually this is used by many hackers. So it sounds like a good idea to use the same tools that hackers are doing. And typically, if let's say you have like a couple of tests or a few tests, but you don't have like a lot of tests, you can use TrustInSoft at level 1 coupled with AFL. So AFL is going to generate a lot of tests. All of those tests are going to be thoroughly scanned by TrustInSoft, and in this way, we are going to get some undefined behavior. Typically, what we did, it was like a year ago, we took Wireshark as an example. It's a very popular open source framework to analyze IP packets, but you can also use it as an intrusion detection system if it runs live. So we downloaded the source from GitHub. We launched, there was 44 tests. We expanded those 44 tests to 10,000 tests. And each of those 10,000 tests were run through TrustInSoft. And this way, we found 13 undefined behavior. And of course, we gave them to the maintainers. We say, oh, thank you, guys, and they perform some correction. And indeed, fuzzers, they help us to be even more powerful at level 1.
Thank you. Anything else from the team? Any other question from the members? No. Okay. So if people wants to find you in the web and online, where can they find you?
So if they type my first name and last name, hopefully that should work on Google. I have otherwise a Twitter. I think I'm going just to share my screen. And you got my Twitter handle, which is right here, FDEREPS, which is another way of finding me, or LinkedIn should be fine as well. So Twitter, LinkedIn, or Google with my name should hopefully work fine.
Okay, thank you. Thank you, Fabrice. It was very interesting. Thank you for the talk. And thank you, everyone, joining me this noon hour. And see you next time. Thank you, Fabrice. Appreciate it.
Bye. Take care. Thanks for inviting me.
Take care. Take care. Bye-bye.